Great. So good morning, afternoon, evening. Here in Thailand, it's 10 p.m. It's always my favorite time for these webinars, but we want to make sure we also have the colleagues from the US. It's early morning there, and Europe are the lucky ones. And then here in Asia, and I think the people in Australia, unfortunately, it's in the middle of the night. So in this science webinar, Siriel, Saladin, and Kazbek Tursun from our science team will discuss approximately 15,000 days of collocated measurements, where we collocated and deployed AirGradient monitors alongside reference-grade PM2.5 instruments in more than 10 countries on 6 continents. With this session, we look at the sensor performance at the general level, share some of the most interesting findings that come from how the performance is evaluated and the sensors actually themselves. So to introduce the speakers, first Siriel will start. Siriel is currently doing his PhD at the University of Cambridge on the topic of air pollution from car tires and brakes, and expects to graduate this year. And then Kazbek is also doing his PhD at the Al-Farabi Kazakh National University, expected to graduate in 2027 and working on the topic of source apportionment of ambient air pollution in Kazakhstan's major cities. So we're going to have first Siriel, then Kazbek, and then we going to have quite a number of time to just muting people. We will have ample time then to have a Q&A session in the end. So if you have any times you have questions, feel free to put them into the chat, and then we will ask the speakers at the end after Kazbek's presentation. So without further ado, I would say, Siriel, the floor is yours.
Thank you, Joachim. Thank you, everyone, for joining in today. So Kazbek and we will be talking about performance and accuracy of our low-cost PM2.5 sensors in the context of outdoor air. So it's about the open air model, which is shown here. It uses a PM2.5 sensor from Plantower. It's the same one which is also used by our indoor model. So the insights that we gained from this collocation is somewhat transferable to the indoor model, but we didn't test it. So we focus here today on outdoor air. At AirGradient, we want to know how accurate are these sensors and how can we improve the accuracy. And to do that, we do a lot of collocations. What is a collocation? So what we do is we take our low-cost monitors, there are 3 of them shown here in the picture, and we locate them next to a reference-grade monitor. In this example, it's a monitor in Chennai in India. And then we have the data from the low-cost monitors and the data from the reference, and we compare them against each other. And ideally, the 2 data sets are the same. We do these collocations not by ourselves. So this is a collaborative effort, and I cannot emphasize that enough. So we collaborate with many partners around the world, and because of these ongoing collaborations, we are able to do all this testing. So we are very grateful for all these partners that do that with us. At the moment, we have collocations going on all over the world. They're shown here, and today we will be talking about the locations highlighted in red. Why? Because that's the locations where we have the data processed. As you imagine, it generates a lot of data, and it does take time to actually process all that data. So as an overview, we have, I think, around 14 locations today that we will be discussing. We have, for example, Sydney in Australia, Brussels in Belgium, then Edmonton, Canada, Ottawa in Canada, Bogota in Colombia, then as said, Chennai in India, Johannesburg, South Africa, Zurich, Switzerland, Chiang Mai, Thailand, 2 locations in London, 1 in Cambridge, UK, and then Court and Bellingham, that's 2 locations in Washington State in the US. And in all these locations, we have 1 or up to 6 AirGradient low-cost sensors collocated with a reference grade monitor. If you're interested, you can see the monitors here that are being used as a reference. And on the last column, as you can see here, you see that the deployment in some cases started quite a while ago. So the first ones were in Chiang Mai, Thailand, in January 2023. So now for 3 years, and it's still ongoing. As you can see, there are the youngest deployment was, I think, August 2024 in Colombia, Bogota, which means that all the insights we gained from these data sets is based on sensors that have been deployed before August 2024. And as you might know, we at AirGradient, we currently do batch-specific calibrations in Chiang Mai in Thailand with our reference grade monitor in an aerosol chamber. And we don't include that in this presentation today because we don't have the data yet. We didn't do as extensive testing with these monitor-specific calibrated monitors compared to the monitors that have been deployed before. So keep that in mind, and with all these locations together, we get a total of something like 15,000 days of outdoor colocation from 41 sensors, low cost, in 10 countries on 6 continents. Okay, so how does it look like? I want to show you some random time plots from random locations. So this is 2 weeks of data from Court in Washington State. We see the PM2.5 concentration on the y-axis over time. And we see in blue the low-cost data from AirGradient. And this is raw. It is not corrected. It is not calibrated. It is out of the box as provided by Plant Tower, basically. Then we also see the reference data in red, which we believe is most accurate. So that's what we assume is ground truth. And in this example, we see that these 2 lines do not perfectly agree with each other. So we see that the trends are pretty much the same, but we see that the blue line is systematically higher than the red line, especially at higher concentrations. For example, here at something like 20 micrograms, the low-cost sensors are systematically higher than the reference. It's different at low concentrations. So here in this time period, actually the agreement is not, the agreement is much better than at high concentrations. What you may not see directly is that there are actually 2 low-cost sensors shown here in blue. So there are 2 separate blue lines, but they're so close to each other that they are hardly to spot. So it means that in this example, the 2 AirGradients that are located next to each other, they pretty much report the same numbers. Let's take another example from Brussels in Belgium. And again, it looks relatively similar. So we have multiple AirGradient sensors in blue that report very similar numbers. And again, they seem to be higher than the reference, especially at higher concentrations. Then an example from Chennai in India, and it again looks relatively similar. Then in Chiang Mai in Thailand, where again the AirGradient systematically overestimate. Edmonton in Canada, here we have wildfires. That's one of these wildfire spikes. And again, the AirGradient overestimates. Zurich in Switzerland, it again looks relatively similar to the others on first glance. And London in England and Johannesburg in South Africa. And the general picture that we see in these locations on typical weeks is relatively similar with respect that all these locations are quite far away from each other in some cases. We talk about different continents. We talk about different humidities, different temperatures, different maybe different aerosols, different aerosol composition, different particle size. And yet the overall picture, if we look at it like this, is relatively similar. And we can say that on average, the emphasis is average. So on average, the AirGradients raw, they overestimate something like 60%. And this is nothing new. This is actually established in this field because it is known that the PMS 5003 on average, the raw data, it tends to overestimate. And this, for example, has resulted in different correction algorithms. For example, the US EPA developed an algorithm based on a lot of data from the same sensor, the PMS 5003, in outdoor environments. And they came up with this, it looks a bit complicated algorithm because it treats different concentrations differently. But what it basically does is it just brings the numbers down. And it does that in a very efficient way, and it does quite a good job at doing that. So it doesn't introduce any jumps, and it makes sure that the low numbers that tend to be already quite agreeing with the reference, that they're not further reduced. But if you want to say it in simple terms, then you can say that in average, this algorithm just divides by the numbers by 1.6 to get the numbers down. And it also accounts for humidity, as you can see here. So it reflects the influence of humidity, and I will talk about humidity later on. Let's have a look in an example that we have, like here in Edmonton, Canada, where the raw data on the left side, again, the blue line, AirGradient, is overestimating. And now if we add the US EPA correction, the numbers come down. And they come down in a way that the small numbers, they do not come down. And we can see it on the right that now the agreement between red and blue is improved. So they agree quite well in this example. What about the other locations? Let's take a look on this table. So the US EPA, they have targets. What agreement between reference and low-cost sensor is considered good? And they have the target that for daily data, 2 sensors are considered to agree reasonably well if the RMSE is below 7 micrograms per cubic meter or the NRMSE is below 30% in terms of accuracy. You don't need to know what this means. It's just important to know that we want to be within these limits. And if we look at all the locations, after correction, here in the last column, we see that of the correction, 13 of the 14 locations, they meet this US EPA target. That's, I would say, encouraging. What you also can see is this column here, and I want to draw your attention to that. What does this mean? So not every location responds differently to the US EPA correction. So for example, in Belgium, Brussels, we have an NRMSE improvement factor of 3, which means that the NRMSE improved 3 times when we used the US EPA correction algorithm. And you can see that all these numbers are bigger than 1, which means that in all locations we have an improved agreement between reference and low cost, except for Australia, Sydney, and Colombia, Bogota. So there we have numbers below 1, which means that as a result of the US EPA correction algorithm, the agreement between low cost and reference, it was reduced, which is interesting. So why is this happening? There could be multiple reasons. Let's take a look into the raw data from Bogota and Colombia. And now we can see that the blue AirGradient line and the red reference line, they already agree reasonably well for raw data, which we did not observe for the other locations. And if we look at the case in Sydney, Australia, we again see that the AirGradient data is not higher than the reference. So for some reason in Bogota and Sydney, we do not see this typical overestimating behavior from the low-cost sensors. Why? So it could be conditions like humidity or temperature. It could be related to the aerosol. Maybe we have different particle size distributions, maybe different composition. An interesting observation is the following. So in Bogota, Colombia, we use the Thermo FH62C14 as a reference monitor. And in Sydney, we have the Thermo 5014I. And these two reference monitors, they are beta attenuation monitors from Thermo. And from all the locations that we have investigated so far, there are only 2 locations where we have beta attenuation monitors from Thermo. And these 2 locations are Bogota and Sydney. The only 2 locations where we do not see this disagreement between raw, AirGradient, and reference. This could be a coincidence, or maybe it is not a coincidence. We don't know. But we investigated and we tried to understand like how accurate are these reference monitors, because we assume that they are accurate and they are ground truth, but every method comes with uncertainties and limitations. So we tried to look for some evaluations that looked into the accuracy of these monitors, and we didn't find many publicly available documents. What we found was this one report with the US EPA, where the accuracy of the FH62C14 monitor was evaluated. That's the monitor that we use in Bogota, Colombia. And it has been tested here in a chamber experiment using ammonium sulfate as an aerosol. And the authors, they wrote that the slopes of the regression lines for the 2 monitors that have been tested, they were around 1.6, indicating a positive bias of about 60% relative to the FRM gold standard filter method. So in other words, in this experiment under these conditions, it was found that this reference monitor overestimates by 60% for ammonium sulfate, which is not representative of ambient PM, and we do not know how this finding translates to outdoor conditions. But it could be that if the sensors overestimate indoor with ammonium sulfate, that they also overestimate outdoor. And it has been reported a couple of times now that although we often assume that reference monitors, they measure the same, it has been reported that they sometimes do not measure the same. Here I want to refer to this one study where the authors in 2024 actually systematically evaluated the agreement or the accuracy of reference grade monitors for PM2.5. I can recommend this paper. It's very insightful, in my opinion. And in this publication, the authors, they provide different plots. I've taken one of them. It is shown here, and here we see the data from different reference grade monitors that have been compared to the gold standard filter method. And then if we have the ratio between the FEM monitor, those are the FEMs, and the ratio between FEM and then the gold standard FRM, then ideally the ratio would be 1. They would report the same. But the authors, they found that based on what reference it is, they see systematic differences. For example, the T640, the Teledyne, it was found to, on average, overestimate by 20%. It also comes with quite a range, in some cases up to 50% overestimation. The MET1 with the beta attenuation monitors, it was found that on average it actually agrees quite well with the FRM method. What does it mean now for what we want to do? So we do the collocations with the assumption that the reference monitors provide numbers that are ground truth. But we see that there are differences between different monitors. It's also reported here, and it means that based on which reference monitor we choose for the collocation, the perceived accuracy of the low-cost sensor will be different. So we might end up with more or less agreement based on how we do the testing. Another important factor which I want to elaborate on is, for example, the influence of time resolution. So here is an example from Enaccords in Washington State, where a beta attenuation monitor from MET1 is used, and we see the AirGradient data in blue and the reference data in red. And the correlation coefficient between the two data sets for hourly data was found to be 0.58, which is rather a bit low. So we usually want it to be higher, ideally around 0.9. So it could raise the impression that these two sensors do not agree or do not correlate with each other. But if we look at it more closely, for example, here, we see that especially that the reference monitor, the red line, it is very noisy. So you can see how it jumps around and it's not stable, especially at low concentrations. So the blue line, the low-cost line, is much more stable. And this is not surprising because the blue line is based on light scattering, which is very sensitive to low concentrations, whereas the red line is based on beta attenuation, which is not sensitive to low concentrations. So we have a lot of noise, and this is known for beta attenuation monitors. And because of that, we see quite a poor correlation between the two lines. Now, one way to handle this is just simply changing the time resolution. So now if we do daily averages instead of hourly, then we see that the correlation coefficient, it improves a lot. So now we have 0.85, indicating good correlation between the two. And you can see here now, in this period of low concentration, there is no noise anymore because it has been smoothed out. Then the next slide, I want to talk about the influence of humidity, which is often mentioned in the context of air quality monitoring with PM2.5. And it is known that relative humidity, it affects the accuracy, or it affects the readings in general. And we confirm that, we also see that, but we don't see a very big effect from humidity. So this is an example from Cambridge in the UK, where we have the PM2.5 readings from the reference on the y-axis, and on the x-axis we have the low-cost data. And then for every point, we know the humidity that has been that was there at the time, and the color indicates the humidity. So if it's blue, then it means it was relatively humid, and if it's red, then it was relatively dry. And we can clearly see that there is a pattern. So the blue lines, they tend to be on one side, and the blue points tend to be on one side, and the red points on the other side. So there is an effect. And when we quantify it, we get something maybe like a few percent of an effect, not tens of percent. And the finding of relative humidity having relatively low effect, it agrees with the US EPA correction algorithm, which accounts for humidity. We can do simple examples because they provide the math. So we can just, for example, calculate the corrected PM2.5 values for a raw reading of 100 micrograms using one end of the humidity spectrum, using 0% humidity. And then the math gives us a corrected PM2.5 value of 84 microgram. And then for the same raw concentration, but with the other extreme of humidity, we get 76 micrograms. And this is a significant difference, but I wouldn't say it is a drastic difference, given that we talk about the full range of humidity in this example. So to wrap it up, this is my part. I think it can be helpful to differentiate between factors that influence the perceived accuracy of low-cost monitors and factors that actually affect the accuracy of the low-cost monitors. And in terms of the perceived accuracy, I think the most relevant factor that we have found so far is the role of the reference monitor in terms of noise and in terms of slope, so just bias, because not all the reference monitors report the same. Then we see a lot of influence from the time resolution that we choose. Based on how we evaluate the data, the results will be better or worse. And also the role of the PM2.5 concentration is quite impactful as we see it. Not just the absolute concentration itself, but also the range of concentration. So if we have a colocation where the concentration of PM2.5 does not change a lot, it's quite stable, then the results will be very different compared to a colocation that actually has a very dynamic PM2.5 concentration, because the conditions are not the same. And these metrics like R squared and RMSC, they're really good at capturing dynamic conditions, and sometimes they're really bad at capturing static conditions. So I would say that these factors here, they have high impact on the performance evaluation of air quality monitors, but there is relatively low awareness of these factors. Then on the other side, there are these factors that actually influence the accuracy. And there, based on our current understanding, we would say that the aerosol composition is the most relevant one, especially the particle size distribution, but also the density of the particles, because as you may know, all optical sensors, whether low cost or reference, they do not measure mass. Instead, they count particles and they measure size, and then they calculate mass, assuming a density. We see that humidity does play a role, but maybe not a very big role. And we so far have not seen effects from temperature. Overall, I would say that in this data set, we see differences between the US EPA corrected low-cost data and the reference data. But these differences that we see, they are no larger than the differences between the reference instruments themselves that we see and also have been reported by others. So that's for the US EPA corrected data. Again, we currently do not know how the monitor-specific calibrated performance is from the sensors that we currently calibrate in Chiang Mai in our chamber. But speaking for the US EPA corrected data, I think that's our finding at the moment for average performance. It raises the question, what about performance over time? Because the sensors, they might lose accuracy as they drift, for example. And that's the topic that Kazbek will elaborate on. So I pass it on to Kazbek.
Thank you, Siriel, for insightful presentation.
I'm going to stop sharing. So it's all yours.
Thank you. So, hello. Good day, everyone. My name is Kazbek, and I will talk about the performance and long-term stability of AirGradient PM2.5 sensors. How do you hear me? Okay. So, before going on, I would like to talk about the metrics which we use for assessment of PM2.5 sensors in AirGradient. So we actually follow the EPA guidelines, and the first metric, this is a precision, and precision is responsible for the agreement between sensors of the same type, so how close the readings are between the sensors. Accuracy, on the other hand, is the closeness of the readings to the true value. So as we see on the picture, so sensors can be low accuracy but high precision, but they will not close to the true value. Otherwise, they can be close to the true value, but the spread can be high. And the ideal case is when we have high accuracy and high precision, as shown on the bottom on the right. So how do we calculate? How do we know what precision, what metrics to use? Precision is usually calculated from standard deviation. However, this is absolute value, and in order to make it more easier, more convenient to calculate, to compare, we can use the relative standard deviation, which is actually a coefficient of variation. The formula is the same. So we just use standard deviation and divide it by mean concentration from all the sensors. So this shows the spread in percent. And according to the EPA target, the coefficient of variation should be less than 30% between the sensors. What about accuracy? We can measure root mean square error This is RMSE. This is also absolute error. Or we can use normalized one for better comparisons. For like, it's more convenient to use the metric which is in percent. Normalized root mean square error, which is calculated by dividing RMSE on the reference mean concentration. So the accuracy is measured between sensor and the reference. You don't have to keep in mind this formula just to know how like what it uses. For example, RMSE error is using sensor readings and the reference readings. So, and all these metrics can be calculated in Python, in Excel, and like other stuff. According to the EPA, the RMSE should be less than or equal to 7 microgram per meter cube, or it can be less or less than or equal to 30%. So other metrics include R square. This is the coefficient of determination, and this shows how trends from readings of sensor and the reference agree between each other. So it is correlation, and it have to be higher than or equal to 0.7. Slopes and intercepts. This is the coefficient of linear regression, the simple linear regression. So slope is responsible for sensitivity. The value is lower than 1. They usually shows underestimation of the measurings. Slope higher than 1 shows overestimation. So ideally it should be 1 plus minus 0.35 according to the target of EPA. Intercept is the readings. It's actually readings of sensor at the 0 concentration. And ideally, it should be between -5 and the 5 microgram per meter cube, not more. So coming to the results, this is the readings from 4 sensors placed in Chiang Mai, Thailand. And if we look to the precision on the bottom, coefficient of variation is equal to 3.9%. This is very high precision between 4 sensors, which is less than 30% of EPA targets. So on the left side of the picture, we can see the time plot with readings, with raw readings of AirGradient, with EPA corrected readings. And this is the averaged readings between 4 sensors. And we also can see the reference readings. As Siriel just said, the raw readings tends to overestimate. So that's why we can clearly see that there is a systematically higher, but the EPA corrected ones fit well to the reference values. On the right side, there is scatter plot showing the metrics also. So R square is pretty ideal, 0.98. RMSE which is normalized root mean square error, is 13.6%, which is less than 30% of EPA target. However, RMSE is 11.18, which is higher than 7. But according to the EPA target, we can use either RMSE or un-RMSE. So this is okay. We also can see the regression equation here. The slope is 1.18, which is in the targets, and intercept is -10, which is higher than, which is out of the targets of EPA. So, but the same analysis was also made for 10 rest 10 locations around the world. So we can see the scatter plots. There is EPA corrected concentrations of AirGradient readings and the reference readings on the x-axis. These collocations were chosen on this criteria. So first one, there should be 15 days of stable and continuous readings. Sorry for misspelling here. And also, there should not be event affected days. So there was 11 locations. And from these 11 locations, we have this table. So this is an overview table from 11 locations worldwide. Here we can see the metrics and the quantities of these metrics. So coefficient of variation on average between 11 locations was 6.8. And we also can see the ranges here, which is okay. So the last column shows the locations that meet EPA target. So from 11 locations, all 11 locations were met from the perspective of precision. Accuracy was calculated, absolute accuracy, relative accuracy here, and we also can see average values, and we also can see the ranges. So to generally look at this table, we can conclude that most of locations were the readings from most of locations were met EPA targets. However, some metrics, some individual metrics were out of the EPA targets. And this shows the overall stability, overall accuracy of the PM2.5 AirGradient sensors. However, sensors tend to change. So even the sensor is accurate, it tends to change over time. So for example, there can be no change in concentration at all, but the sensor can give a systematical drop or increase in concentration. So that means there is a drift. And so we should assess drift in order to be sure that our sensor performs stable over time. For this test, we chose London location, where we have 2 years of stable collocated data with reference. So, and looking at these results, we can conclude that there was no systematic drift over the 2 years because there was no systematical increase or decrease in concentrations. In the slopes, sorry, this is the EPA guidelines, which shows that the slope, a monthly slope calculated for each month, shouldn't increase or decrease systematically. So we also can look at the general graphs with the other metrics. For example, here we can see RMSE change over time, the R-squared change over time, and the seasonal variations of the concentrations for each sensor. So there are 4 sensors in London, and all of them didn't show any high rapid leaps in concentrations, didn't show any systematical drop or increase in concentration. So we can conclude that this like 4 sensors in London, they didn't overcome with the drift. So we answer to this question: do the sensors perform well and remain stable? Yes, they can deliver reliable long-term measurements once they calibrated. But this study was made on the base of 11 locations with 50 days of continuous operating sensors, and the conclusions was okay. However, individual units can still behave differently, and for monitoring, for being sure that the sensor operates well, there is a need in analytical quality control. Thank you for attention.
Great. Thank you, Kazbek and Siriel. We already got a couple of questions in the chat, and I'm trying to randomly pick them out, and hopefully we have enough time to go through all of them. So keep on putting them in if you have more questions. So maybe we can start with one question from Dima, probably towards Siriel. What normalization methods do you use to calculate NRMSE?
So the numbers that I referred to were based on daily data, which is also suggested by the US EPA. And it uses the data from the reference to normalize. So it's the RMSE divided by the mean from the reference.
Okay, and then actually we can just continue with another question from Dima. US EPA correction is applied to the raw CF1 channel of the plant tower. From AirGradient monitor, did you use the default atmospheric corrected signal or also the CF1?
So all the PM2.5 readings that we provide on the AirGradient platform is CF atmosphere. And the correction is also based on the CF atmosphere. And there are different versions from the US EPA correction algorithm, and they have been revised over time. We use, I think, equation 4, if I'm right. And equation 4, to my knowledge, is based on a CF atmosphere. I think it changed. Initially, it was different. If you know something else, then please let us know.
Good. Then there was a question I can actually answer, like how were the monitors connected? So this was the first version of the open air model. So that was connected to power and to Wi-Fi. So it wasn't the new model with the solar panel or the cellular version. So one question or remark from Anton, surprising, and I think that refers to the different kind of results from the reference monitors. Surprising, I thought this reference monitors must be calibrated individually on site, like other measurement devices. Not sure, Siriel, if you know about these operational procedures.
Actually, I do not know. Do you know, Joachim?
No, I don't know too, but yeah, it will be interesting to find out how actually reference devices are calibrated on site and compared to what's the gold standard and probably in the end. So let's see, what else do we have? Rod made a remark that the structure in Sydney seems to look different. I'm not sure if you noticed that, Cyril.
Yeah, also the slope is different. So if we compare Bogota and Sydney, then the numbers in Bogota are different. Although both these locations, they use a beta attenuation monitor from Thermo. So we do not know why there are these differences. We also do not know how these two monitors from Thermo would compare to each other in the same conditions.
Good. Then Paulo made a remark about the South African monitors seem to be an outlier. And it's quite possible that the stations there might not be well calibrated or maintained. We had one station there, I think Vanderbilt, Cyril. Is that something you might also consider, that the reference might be wrong potentially there?
So this case from South Africa, which is Vanderbilt Park, close to Johannesburg, we do have reference, for example, reference temperature data. No, I need to correct, and a reference humidity data that is being provided to us. And this reference humidity data is unplausible, physically unplausible, because it jumps from 0 to 100% within 5 minutes, and then it goes back to 0. And this has been going on for months, and we couldn't figure out what's going on there. The PM data on the other side, it looks physically plausible, but we do not know if these readings are accurate or how accurate they are. So in our current colocation, we only have, I think, one location where we use a GRIM as a reference, and that's the one in Johannesburg. So we don't know if this finding from Johannesburg is systematic, or if it's related to local conditions, if it's the aerosol, or if it's the reference.
I can add that from Johannesburg, we had 373 days of measurements collocated with reference, and the statistical metrics are okay. They like fit EPA targets well, but I assume that this is normal behavior because of the high concentrations in that place. From all of locations, this was the third most polluted.
So also the N-RMSE is within target?
No, N-RMSE is like around 60. So this is higher than EPA.
Yeah, but the rest is within target.
Yeah, I mean the R squared slope looks okay.
Okay.
However, there is some issues in accuracy, but in general we can say that it's okay for taken time period.
Yeah.
Okay, one question from John, maybe also towards Kazbek. Do sensor readings in locations with high levels of particles deteriorate more quickly than in clean locations? So it's probably, do we see more drift in more polluted areas or not? Or did you look into that?
We look into the Chennai in India, and the issue was that we didn't have enough time of enough data points. So we split. Usually, we do a drift analysis. We split into months, but however, in case of Chennai, we split it into the weeks in order to see like pattern. Concentrations were high, but in 2 months there was no drift, no evidence of drift. Unfortunately, we don't have more data points and time range, like time diapason, how to say, like to say clearly that if we have drift or no.
One interesting thing from Antoinette, I think I can actually answer. Did you account for ambient humidity versus the internal humidity of the device? The unit generates some heat during operation, or it might be affected by local heat sources. So this is quite interesting because for the open air monitor, we use the internal sensor from the plant tower module, it's the PM2.5 And what we see is, I think, around 10 percentage points lower humidity than ambient. So what we think is actually probably the relatively high impact that the low impact we see from relative humidity is probably because in a way the sensor module just conditions the air and reduces the humidity before measurement. So that's a potential positive side effect from this. So let me see, what else do we have? Let me just quickly have a look. So John was asking, can you give reference to the full nonlinear EPA correction paper? And have you compared AirGradient with purple airs? Not sure anybody, Siriel or Kazbek can maybe.
So I can answer the second question. Yes, we did compare purple air and AirGradient monitors. And we found that they are very similar based on what we have tested. So in terms of PM2.5 and also humidity. And that's not surprising because the purple air sensors that we have used in these tests, they are also based on the PMS 5003, which is the same sensor that is being used in AirGradient.
Good. Interesting questions also from Matt. Are there other countries or regions that have studied these correlations and produced correction algorithms that are in agreement and verify the US EPA findings? So I think that's maybe kind of localized correction factors, potentially.
So I'm aware of a couple of scientific papers where scientists have came up, they developed correction algorithms. I'm not aware of countries or environmental agencies that did that besides the US EPA.
Great. So we are a minute before the close of the hour, so I want to wrap this up. I might have missed one or two questions potentially. Then just contact us. There's a support form on our website, and then we can forward that question to Siriel and Kazbek and can answer that. Many thanks for having so many people here joining us today. I think it was really interesting. Also for me, even I am supposed to know all of that, but even a few new things came that I really appreciate it. So many thanks to Siriel and Kazbek. It's really great to have you on the team and to really like help, I think, us and also people that use our monitors to really understand what's going on, not only in Europe or the US where we have a lot of these co-location data, but also in countries like here in Asia, Africa, or South America. So many thanks, and also many thanks for the nearly 80 or 90 people we had joining us today. And we will put this recording obviously up onto our channel in a couple of days, and then in case you missed a part, you can rewatch this. And other than that, I'm looking forward to see you next time. Many thanks.